And if y'all don't have anything specifically for me, we'll get started with class today. And let's start on the whiteboard, which is the only place we can go. Okay. All right, now I've got to move things around. There's a taskbar at the bottom that blocks the whiteboard. There's a taskboard at the top that blocks the whiteboard. And there are your pictures here, okay, or not pictures, your blocks that show that you're in the class. And then the whiteboard is not spaced well, so I have to move it to as far to the left and up as I can, so I have the maximum writing space. All right, so before we get started, any questions on anything we've done so far? Okay, now if my mark is right in the book, we're in Chapter 2, Matrices, Section 2.2, Properties of Matrix Operations, and we're on the top of page 56. We had done Theorem 2.4 and example 6a, but we didn't get 6b done. Is that where y'all had your memory to be? So let's do B. That's starting with the identity matrix here, the I3 identity matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1. Remember, what is the identity matrix? The main diagonals are all 1s, 0s, every place else. Okay? And we're multiplying this by a column vector or column matrix, minus 2, 1, 4. Okay? Now, first thing you should ask yourself, can you legitimately do that matrix multiplication? Well, this, of course, being I3, is going to be a 3 by 3 matrix, always square. To be an identity matrix has to be squared. This is a 3 by 1 column matrix or column vector. The 3's match, so you can do it, and that gives you a 3 by 1 result. What's left over after you cross out the interior ones, that gives you, so you get a 3 by 1 left over. Well, the size is right anyway, so let's do the calculation. That would be the first position here, the 1, 1 position. First row, first column, so do the first row of I by the first column of this column matrix, the only column that's there. So it's minus 1 times minus 2 is minus 2, plus 0 plus 0, that would be a minus 2. The 2, 1 position here would be the second row here by the only column here. That would be a 0 plus 1 plus 0, that's going to be 1. The 3, 1 position here will be the third row here, the only column here. That would be 0 plus 0 plus 4. Sure enough, that reproduced that matrix. Okay, exactly, precisely. Now, what they jump to next just seems out of place, but it's perfectly fine. But it has nothing to do with what we're just talking about. It says, for repeated multiplication of square matrices, we use the same exponential notation as real numbers. So this has nothing to do with what we were just doing, but it's this. So if you had A to the first power, that's just matrix A. If you had A squared, that means matrix A multiplied by matrix A. Now, most of the time you can't just do any old, but if these are square matrices, same number of rows and columns, then yes, you can multiply them. Because if this is, say, a 3 by 3, that's a 3 by 3, then your answer is going to be a 3 by 3. And then you can do again. And A cubed would then be A times A times A. And this would be a 3 by 3 by 3 by 3, giving you a 3 by 3 times a 3 by 3 gives you a 3 by 3. So you always stay that same size as long as these are square matrices. So A to the K would mean that you multiply A by itself K times. 1 time, 2 times, 3 times, 4 times, dot, 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 up to K times. Okay? That would be A to K. You have K factors of A. Now, here's the only key here. What do we mean by A to the 0th power? Just like in real numbers, that would be I sub n. Whatever your size A was, it had to be a square matrix, that would be the identity matrix. Okay? So that's the only key to the I here. Okay. Now, excuse me, I've had worked outside all weekend. I mean, out mowing ragweed and goldenrod, and I can't even name the number of weeds I was mowing, and grasses and things like this. So my head's a little congested. That's the other thing I had to run down to the restroom for, see if I could clear some out. It's clogging up, and then to the cooler temperature today I think is contributing. So excuse me just a minute. I don't know if that really helps, but the carbonation actually makes it feel like I can breathe a little better. But anyway, all right. Now, these properties here lead you to define some other properties. And since this section 2.2 is properties of matrix operations, here are a few more. What if you had, where is my pen? There it is. Okay, I found it. Okay. If you had A raised to the jth power times A, same base, raised to the kth power, what would that mean? Well, this would be J multiples of A. This would be another K multiples of A. Now you'd have a total of J plus K multiples of A. So that would mean that's the same as A to the J plus K. Just like we have with real numbers. Okay? Now, the next one, what if you had A, come on, where's my pen? It just keeps, there it is. Okay. A to the J, and you're raising that to the K power. Okay, let's keep something sort of small now. Let's say J is 2, so you have A times A, that's A squared. Okay, but K, let's have that kind of small, like 3. Okay, so it'd be A times A times A times A times A times A. Well, how many A's would you have? 6. Well, that would be the same as 2 times 3. And sure enough, that is, there it is. That is the rule. That would be A to the J times K. When you're multiplying matrices, same matrix, different exponents, keep the matrix, add the exponents. When you're raising a power of a matrix to another power, keep the matrix, multiply the exponents. Same thing we had for real numbers. Okay? Now, J and K here are non-negative integers. They could be 0, 1, 2, 7, 14, any non-negative integer. No negatives. We haven't talked about those. They don't even work, so don't even mess with them. So let's see if we can verify that with a matrix. So let's clear this screen. Anyone have questions before I clear it? Okay. And here's example 7. Here's matrix A. 2, 2, -1, 3, 0. Okay. Now, for that matrix, figure out what A cubed is. And there's no easy way to do it, folks. It's just brute force. Okay. I can write it down fairly easily, but to do it, you have to slug through it. Okay. That would be 2, -1, 3, 0, if I write it down correctly, times 2, -1, 3, 0, times 2, -1, 3, 0. A cubed. It doesn't matter which one you do first. You could do these two times that one, or this one times the product of those two. It doesn't matter. Okay, so let's do these two first. Certainly that's going to be a 2 by 2, and we'll multiply it by 2, -1, 3, 0. Oh, here comes James. Perfect attendance today, folks. Way to go. Fantastic. In my class right before this one, I had 1 absence is all. And that was from out of a class I think they're down to 18 or something now. So that was a great attending class. Y'all are perfect attendance. Way to go today. Okay. So let me get my pad back and close out that. Okay. So let's do the 1 entry here. That'd be the first row here by the first column here. 2 times 2 is 4. Minus 3 would be 1. The 1, 2 entry here would be first row, second column here. That would be a minus 2 plus 0. That would be a minus 2. The 2, 1 entry here would be second row here, first column there. That would be a 6 plus 0 is 6. And then the 2, 2 entry here, second row, second column, and that's a minus 3. Okay, obviously you can do this multiplication too, square. So this is going to be a 2 by 2. And first row, first column, be a 2 minus 6 is minus 5. First row, second column, first row, second column, minus 1. Second row, first column, second row, first column, 12 minus 9 is 3. And second row, second column, second row here, second column there, minus 6. That's what I get A cubed to be. How did they get it? Oh, I moved. Let me go back this entry right here. The 1, 1 entry. First row, first column, that would be 2 minus 6 is minus 4. I said 1 minus 6. 2 minus 6 is minus 4. Let me see if I can erase that. Everything but what I want to erase erased. Minus 4, minus 1, 3, minus 6. Minus 4, minus 1, 3, minus 6. Got it. Okay. Now, I know I asked this question. You probably are sick of hearing me do it, but I teach a few small classes, and some of you are all in the same class, but I can't remember who has what. Do all of you have access to a book now? Yay or nay? Let me know if you don't. Say that again? Yeah, you mean the ebook? Okay, but you do have access to the ebook. And both of the others of you do too? Okay, can you find what we're doing in the ebook easily enough?
I'll just need the page number because I gotta scroll up or down and then next and then next. Like I can't just do it like a normal page.
Okay.
I know the exact page number.
Okay, that's interesting because in some books, some of the students say, page numbers don't do me any good. Tell me what section we're in or something like that. So you need a page number. We're on page 56 in the text. And there's a theorem 2.5. Okay, I heard from Miguel, he has it, or Jesus. Kara, you and James both have books? Yay or nay? They must be not be handy.
Yeah, I do.
You do. And Kara, do you have a book? Oh, you do. Okay, all of you have books. So if it's okay with you, I won't type these in. Okay, we've already done them before, but just a reminder. Okay, Theorem 2.1 says for a system of linear equations, precisely one of the statements below is true. One and only one. Okay? Either that system has exactly one unique solution. Just one. Now this is however many equations you have, however many unknowns you have, either that system of equations has exactly one solution, or it may have an infinite number of solutions, or it may have no solutions. Absolutely none. It won't have just 3. It won't have 17. It won't have 435 solutions. It'll either have 1, 0, or an infinite number. No matter how big your number, infinite number. Okay? Yes.
I didn't really understand how you did this.
What I just said?
No, not what you said, but this work problem you were just doing.
Oh,
You multiplied
yeah.
first two.
Okay. Yeah. Okay. All right. I wish I had 2 markers. I've always wished this. What we have is a raised to the 3rd power, meaning you multiply a times a times a. So those 3 are all the same. You got that? Okay. What I did was multiply these 2 together first. This is a 2 by 2 by 2 by 2. You're going to get a 2 by 2. So what you do here, this entry right here, the first entry here, is first column, first row. So you do the first column of the first one by the first row of the second one. That's 2 times 2 is 4, plus a negative 1 times 3 is a negative 3. So 4 minus 3 is 1. Okay? This entry here is the 1, 2 entry. So you take the first row here, second column here, matching what you're going for. It's 2 times negative 1 is negative 2, plus 1, negative 1 times 0 is 0, so it's just a negative 2. Okay? This is the 2, 1 entry. Second row, first column, so you do the second row here, that's a 3. Second row here times the first column here, 3 times 2 is 6, and then 0 times 3 is 0, so that's just going to be a 6. And then this entry is the 2, 2 entry, meaning second row, second column, so you take the second row of this one by the second column of this one. It's going to be a minus 3 plus 0 minus 3. Okay, then bring this one down just like it is, and when you multiply these two together, then this is a squared times a. That'll give you a cubed. This is 2 by 2, that's 2 by 2, this is going to be 2 by 2. So again, for the first row, first column entry, this one here, you do first row here, first column here. That would be a 2 minus 6 would be a minus 4. The 2, 2 entry here, 1, 2 entry here, first row, second column is first row here, second column here. That would be a minus 1 plus 0. So that's just a minus 1. Excuse me, I'm losing my voice again. Okay. This entry down here is the 2, 1 entry, second row, first column. So you do second row here by the first column here. 6 times 2 is 12, minus 9 is positive 3. And the 2, 2 entry here, second row, second column, is second row here, second column there, minus 6 plus 0 is a minus 6. So that gave you a negative 4, negative 1, 3, negative 6. And that's the answer they got in the book. Does that answer? Okay, good. Now, it seems like they're jumping a completely different rabbit here. They're going to this. For a system of linear equations, you're always going to have either one and exactly one solution, infinite number of solutions, or absolutely no solutions. You can't have 3 solutions or 15 solutions. You know, it's either going to be 1, 0, or an infinite number. Okay? Now, jumping another rabbit. They just sort of are picking up things and dropping them off. These are all properties of matrix operations. That one we had before, they just threw it back in here again. Now, next property is going to be the transpose of a matrix. Now, this is a pretty simple concept, but it is useful, so get used to it. And what we mean there, the transpose of a matrix is defined to be you exchange the rows for columns. So what if you have A, and A is an M by M matrix? Yeah. Now these don't have to be square, obviously. M by M matrix. The transpose of, and let's just write it out, what that would be. You know, our favorite long, boring thing. Little a sub 1, 1, that means first row, first column. A sub 1, 2, first row, second column. A sub 1, 3, first row, third column. Dot, 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 up to A sub 1, n, because you have n columns. It's a pretty ugly one. Let's see if I can clean that up a little bit. Okay, well, I got rid of too much. A sub 1, n. Okay. Then the second row would be A sub 2, 1, A sub 2, 2, A sub 2, 3, dot, 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 up to A sub 2, n. Okay. Third row would be A sub 3, 1, A sub 3, 2, A sub 3, 3, dot, 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 up to A sub 3, n. And keep doing that until you get down to A sub M1, dot, 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 down to A sub M2, dot, 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 down to A sub M3, and then carry it on over, carry it on down to A sub M N. So everywhere here you had dot dots everywhere. Okay, there's our standard A, M by M matrix. Now, the transpose of A is you exchange that same matrix, you exchange the rows for column. So that would now be what was in the first column is now in the first row. A sub 1, 1, A sub 2, 1, A sub 3, 1, dot, 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 A sub M 1, A sub 1, 2, A sub 2, 2, A sub 3, 2, dot, 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 up to A sub M 2, A sub 1, 3, A sub 2, 3, A sub 3, 3, dot, 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 up to A sub M 3. Okay. I'm sorry. This is way more. Nothing seems to be helping much. Continue on down. Dot, dot, dot. Down to A sub 1 N. Dot, dot, dot. Down to A sub 2 N. Dot, dot, dot. Down to A sub 3 N. It's supposed to be a 3. And then dot, dot, dot. And dot, dot, dot. Down to A sub M N. Everywhere dot, dot. Okay. So this is now the transpose is always going to be an N by M. If the original matrix is M by N, the transpose is going to be an N by M. You're swapping the rows and the columns. Okay? That's what the transpose of a matrix is. Okay? Okay. Now, they have a little discovery off to the side of that. Let's do that discovery and see if we can make any conclusions from that. Here is a matrix A, and that is 1, 2, 3, 4. Very creative matrix here. 1, 2, 3, 4. And you have another matrix B here. And matrix B here is 3, 5, 1, minus 1. Okay. Now it's going to ask us to do some things. The first thing it wants us to do is find A, B, and then transpose it. So let's first do AB. That's the product matrix of A and B. Since these are both square matrices, 2 by 2, the answer is going to be a 2 by 2. Now, do y'all want to do the math for me? What would be your first entry here? The 1, 1 entry. It would be the first row by the first column and add them as you go. 1 by 3, 1 times 3 is 3, plus 2 times 1 is 2, 3 plus 2 is 5. Is that what it meant by the same thing? No. Okay, I thought not. Okay. Only if the one was an identity matrix would it be the same thing. Okay. Neither of those are identity matrix. Next is the 1, 2 entry here. This one will be first row here, second column here, That would be 1 times 5 is 5, minus 2 would be 3. This entry is the 2, 1 entry, second row, first column. So second row here, first column here. That would be 9 plus 4 is 13. And then you have the 2, 2 entry here, second row, second column. Be second row here, second column there. That would be 15 minus 4 is 11. I started to say 12. I thought, where did that come from? Okay, there you did AB. Now it asks for AB transpose. Okay, so AB transpose would then be to exchange the rows and columns of AB. So that would be 5, 3, 13, 11. You just transposed it. You rearrange the rows and columns. Okay. Next thing it asks for is A transpose times B transpose. Well, A transpose would be 1, 3. You tell me, what's the next part? Anybody? Okay, I was asking for A transpose. What's B transpose? You tell me. Three, 1, you exchange the rows and the columns. That's what the transpose is. So it becomes 3, 1 as your first row, because that was your first column here. The second row here will be the second column here, 5 minus 1. Okay? Now, they ask for the product of those two. So A transpose times B transpose would be, obviously, a 2 by 2 matrix. The first entry here, first row, first column, would be first row here times first column there. 1 times 3 is 3, plus 15 would be 18. The 1, 2 entry here, the first row, second column, 1 minus 3 would be a minus 2. Sorry. The 2, 1 entry here, second row, first column, second row here, first column there, 6 plus 20 is 26. Did I do that? Yeah, 26. And then the 2, 2 entry here would be 2 minus 4 is minus 2. So there's A transpose, B transpose. Okay. They also want us to do B transpose, A transpose. So let's do that. B transpose, we already did. That's the 3, 1, 5 minus 1, times A transpose, which is 1, 3, 2, 4. And I hope it's pretty obvious that B transpose, A transpose will also be a 2 by 2 matrix. Let's see what the entries are. First row, first column, that's 3 plus 2 is 5. First row, second column would be first row, second column. 9 plus 4 is 13. Second row, first column. I can't. Sorry, I'm having trouble talking. Okay, second row here, first column there, be 5 minus, I can't read my writing there. Yeah, that is minus 1. 5 minus 2 would be a 3. And second row, second column, 15 minus 4 is 11. Hey, look at that. AB, transpose. Sorry, I put the parentheses in the wrong place. And nobody caught me. What are y'all doing, huh? Okay. AB transpose is the same as B transpose A transpose. Not the same as A transpose B transpose, nowhere close, but it is the same as A B transpose A transpose. Okay? Now, you can go on and do the rest of it, but I think we just showed what we're looking for. So let's do example 8. How are we doing on time? Oh, plenty of time. Okay. So I think I'm going to need to clear the screen. Any questions on any of this before I clear it? All right. It says find the transpose of each matrix. The first one here is matrix A. Matrix A here is 2, 8. The question is, what's the transpose of that matrix? Anyone have an idea? I need to chew on something. I'm not able to. Anyone tell me what the transpose of A would be? Sorry if it's making too much noise, but I need something to loosen my throat. Anyone? Exchange the rows and columns. This was one column here, it'll be one row here. It's exactly the same number, 2 and 8. That's A transpose. B is this matrix here. 1, 2, 3, 4, 5, 6. Very creative matrix here. 7, 8, 9. You tell me what B transpose would be. Anybody? First entry here. First entry here. Are y'all with me or not?
Yes, sir.
Okay, what's the first entry here? 1. Only thing that changes is that what was the first row is now, what was the first column is now the first row. So this will be 1, 4, 7. Give me the second row.
2, 5,
Got it?
8,
Got it. Third row?
3, 6, 9.
Got it. If my pen would get it. Got it. Okay, there's B transpose. Let's do C. Here's C, 1, 2, 0, 2, 1, 0, 0, 0, 1. What would be C transpose? Anybody? First entry?
Is
1, 1, 2, 0,
2, 1, 0,
2, 1, 0,
0, 0, 1.
0, 0, 1. Hey, isn't that what we just had? Yes. Okay. Now, this is a special kind of matrix. When a matrix transpose is the same as the original matrix, we call this a symmetric matrix. That's a symmetric matrix because C and C transpose are identically the same. The rows of one are the columns of the other. Okay, well, that's true of any transpose, but then they turn out being the same matrices. Okay, so let's do D. D is 0, 1, 2, 4, 1, negative 1. What is D transpose? You tell me. Somebody. Anybody.
0, 2, 1.
0, 2, 1.
1, 4, 1.
1,
4, negative 1.
got it. Got it. Okay. Let's see how the book did. They got D transpose right. They got C transpose right. They got B transpose right. And they got A transpose right. Good for them. Now, we're studying properties of matrix operations. Transpose of a matrix is a matrix operation. What are some of its properties? Okay. And I think I may write these down because these are sort of new and kind of important too. So I know you probably can't look at your book or watch the Zoom at the same time you're looking at your book or whatever, so let me write these down. What we have here is A and B are matrices. Obviously with those kind of names. Now, here is a caveat. With sizes such that the matrix operations are defined. I'm going to put appropriate. Okay, with appropriate sizes. Okay, you know what that means. C is a scalar. Okay, then these properties are true. First, if you take the matrix A, transpose the matrix A, and then transpose that transpose, guess what you're going to get? You're going to get the original thing. Because what did you do? You took the matrix A, when you transposed it, you exchanged its rows and columns, And then when you transpose it again, you exchange them back again. So you come back to the same A you had to. The transpose of a transpose is the same. Okay? Number 2. What if you have the sum of two matrices, A plus B? Now this is where A and B, the sizes have to be appropriate. In other words, if A is an M by N, B's got to be an M by N. Otherwise, you can't add them. Okay? Well, what's that going to be? That's going to be A transpose. Oh, wait. If you take that sum and transpose it, then that gives you the transpose of A plus the transpose of B. Okay. Excuse me a minute. I'm having so much problems breathing. Hate to do this. All right. Okay, I've got 16 minutes more trying to breathe. Okay. So that's the second one. And that T really didn't come out too well, did it? Okay. Still didn't come out too well, but so maybe a little better. The C one here. What if you had the scalar C multiplied by the matrix A, and then you were transposing that? Okay? Well, guess what? That scalar C doesn't do anything but come to the outside and then times A transpose. Okay? Because C is multiplied by every entry in it, so all it does is transpose A, C is just still multiplied by it. Okay? And here's the fourth property of transposes. Okay? And this is the one we did in our exploring. If you have the product A times B and transpose that product, now again, the size is important. If A is an M by N, B has to be an N by something. Okay. Well, this says that that's the same as B transpose times A transpose. All right. And that's the transpose of a product. Okay. Goodness gracious. I don't know how I'm going to make it through the afternoon, 4.5 hours of physical science class. But maybe when I eat something, my head will straighten up some. All right. Now, property 2 and 4 can be generalized to cover products and sums of any size, okay, any finite number of matrices. So number 2, if you had A plus B plus C plus D plus E plus F plus G, and you transpose that sum, that would be A transpose plus B transpose plus C transpose plus D transpose. Yeah, that figures, okay? Now, what we're saying is if you had a string of matrices multiplied together, and at some point you better get the sizes all correct. That would be A times B times C times D times E times F, and transpose that product, you're going to wind up with F transpose times E transpose times D transpose times C transpose times B transpose times A transpose. So you could do it for any number of them. They did it for 3 here. Let me just write that out. A, B, C, the product of those transposed is going to be the same as C transpose times B transposed times A transposed. Okay, and that's what they got there. So let's do example 9. And this example, sorry, this example is also given at larsonprecalculus.com. You can see an interactive version of this type of an example. So let's clear this out of the way and do example 9. So they're giving us two matrices. Matrix A is a 3 by 3, 2, 1, negative 2. That's an ugly negative 2. Negative 1, 0, 3. I'm going to erase that if I can and see if I can get that to show up better. Yeah, that's better. 0, negative 2, 1. Okay. Just about out of Coke. I need something. I'm not sure the water's going to do any good, but I'm going to drink it. Sorry. Here is B. 3, 1, 2, negative 1, 3, 0. Now, we need to show that AB transpose is B transpose times A transpose. Now, we did this in the discovery, but those are square matrices, which made sense. These are one square and one rectangular. We got to make sure we can do it. First question, can we do A times B? Well, this is a 3 by 3. This is a 3 by 2. So sure enough, since the inner numbers are the same, then our answer is going to be a 3 by 2. Okay, so let's do it to it. The first row, first column is going to be the first row here by the first column here. So that's 2 times 3 is 6, plus 2 is 8, minus 6 is 2. Okay. The 1, 2 entry here will be first row here, second column here. That's a 2, minus 1 would be a 1. So that's just a 1. The 2, 1 entry here, 2, 1 entry here is going to be second row, first column. Say minus 3, 0, plus 9, that's going to be 6. Okay? I'm sorry. I hate to chew something in the microphone, but so actually I'm almost feeling like I'm going to be sick. So I have to get some of that taste out of my mouth. So sorry about that. Okay. The 2 entry would be second row here, second column here. That would be a -1 plus 0 plus 0. That's going to be a -1. Okay. The 3 1 entry here, third row here, first column there is a 0 -4 plus 3. That's going to be a -1. That's ugly, but I hope you can follow it. And the 3 2 entry here is third row here, second column here. That's a 0 2 0. So that's just a 2. Okay. Now we need to do AB transpose. All right. Anyone tell me what that is? 2, 6, -1. 1, -1, 2. Perfect. Okay. So we know what AB transpose is. Now the question is, what is B transpose times A transpose? Okay. Well, let's do what B transpose is first. Can someone tell me that one? Three, 2, 3, 1, -1, 0. Right? A transpose is going to be 2 -1, 0, 1, 0, -2. We're running out of time, so I'm trying to speed along. -2, 3, 1. Okay, I know that's ugly. All right, so let's multiply those two together. This is a 2 by 3. This is a 3 by 3. The inner two numbers are the same, meaning our result should be a 2 by 3. And at last the size is right for B transpose A transpose. That's transpose should be up a little bit. Okay. Okay. Oh man, I'm just barely hanging in there. Okay. So this is going to be a 2 by 3. The 1 1 entry here is going to be first row here, first column there. 3 times 2 is 6, plus 2 is 8, minus 6 is 2. Okay. Sorry about that stray line there. I'm looking in the wrong places here. Now, of course, yuck, where did that come from? Okay, that was bizarre. Okay, let me move this out of the way. Part of the problem here is that taskbar has gotten in the way. Now we got our eraser here. There. All right, the 1, 2 entry here is going to be first row here, second column there. That's a -1. So it's a -3 plus 0 plus 9. That's going to be a 6. Okay. The 1, 3 entry here is first row, third column. Sorry. That'll be a 0, -4, and I think that's a -1 down there. So that's a, I can't read my writing here. No, that's just a 1. Okay, let me see if I can erase that. Yuck! This device is such a pain in the neck sometimes. Okay. 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 Okay, that's a little bit clearer. So that's a 0, -4 plus 3. That's going to be a -1. Okay, the 2, 1 entry here is second row, first column. That would be a 2, -1 would be a 1, 0, so that's just going to be a 1. The 2, 2 entry here, second row, second column, it's a -1, 0, 0, so that's a -1. And the where is my, there it is, 2, 3 column here is going to be second row here, third column here, and that's going to be a 0, 2, 0, so that's a 2. And sure enough, these two are the same. AB transpose is the same as B transpose A transpose. All right. Now we made it down to example 10. I had hoped to finish example 10 today, but I'm just run out and we're out of time. So we'll pick up there next time. I'm so sorry. Homework exercises here would be any of the odds 1 through 5. They're all at Calc Chat. 7 through 11, they're at Calc Chat. 13 should be at Calc Chat. Odds 15 to 21 should be at Calc Chat. 23 should be at Calc Chat. 25 should be at Calc Chat. 27 should be at Calc Chat. 29 should be at Calc Chat. And any of the odds 31 through 35 should be at Calc Chat. 37 should be at Calc Chat. 39 should be at Calc Chat. Odds 41 and 43 should be at Calc Chat. 45 or 47 should be at Calc Chat. Okay. We're going to hang off the last bit until later, even though we aren't going to do anything else to do it. See if you can figure out 49 and 51. Shouldn't be too bad. They should both be at Calc Chat. But we'll hold off. Well, they're just getting into new stuff here. You can stop anywhere there and we'll pick up and go from there next time. Okay? I'm sorry, I'm feeling so rotten today. Hopefully it'll get better. Any questions? Okay. We'll pick up there, finish 2.2, finally get into 2.3. Okay? I'm going to stop sharing because I'm sick and tired of sharing. Okay? And unless you have any questions, I'll end the meeting for us all. Any questions? Okay, take care, folks. We'll see you on Thursday. I'll see you all tomorrow too, right? Good deal. Bye-bye.